again to my channel. This video or in this class, I am going to teach a topic which belongs to the BSc first year students. And the name of the topic is Electrophilic Aromatic Substitution. Do you have an idea this topic belongs to which unit? So, this is in the second semester of BSc under the unit Benzene and its reactivity. Okay, so in this chapter, generally this is my most favorite topic. That's why I have chosen this topic today coming in front of you to teach this topic. Ready? Now, so before going into electrophilic aromatic substitution, what is meant by substitution? What is meant by substitution? That is nothing but replacement. Okay. Now, what is this aromatic substitution? Substitution in aromatic compounds. So, what is being substituted? So, like, students, for example, if I take the benzene ring, this is benzene ring and inside these are the pi bonds. So, how many carbons are there? 6 carbons. How many hydrogens are there? 6 hydrogens. 1, 2, 3, 4, 5, 6 and each carbon has a hydrogen atom attached to it. Hence, this C6H6 is the formula of benzene. This is an aromatic ring. Okay. Now, what is aromatic substitution? That I am teaching you, right? For example, students, I am writing one of the hydrogens like this. Separately I am showing. That means, students, if we don't show also, that means there is a hydrogen on each carbon. If this hydrogen atom, okay, is replaced by some X or by some Y, that means this hydrogen is replaced by X or Y. So, in this hydrogen, now comes X, okay. So, H is substituted by X or any other group. For example, if Cl is here, chlorobenzene is here. This chlorine, that means this Cl, if it is replaced by some NO3 or some CH3, then also we say that substitution has taken place. Okay, so aromatic substitution is nothing but the replacement of a hydrogen atom or any other group which is attached to the carbon atom of benzene ring. We call it as aromatic substitution. This is of 3 types, students. So generally those the 3 types are electrophilic substitution, nucleophilic and free radical substitution reactions. But most commonly we find in these aromatic compounds electrophilic substitution reactions. Okay, what is the reason why these are common in these aromatic compounds? The reason is benzene or any other aromatic ring, we can say that the pi electron cloud is lying or it lies above and below the plane of the aromatic ring. So, what if it lies above and below the plane of the ring? We can say that these aromatic compounds, that is, for example, benzene ring, it is a rich source of electrons. Okay, so like we say some foods, they are rich in minerals, they are rich in vitamins, they are rich in carbs. Like that, this benzene ring acts as a rich source of electrons. So when it is, so generally, whom do we suggest to take such foods having high in minerals, high in vitamins, whose body is deficient in such things, right? So here now benzene, as it is acting as a rich source of electrons, now this easily attracts the species which are electron deficient. So the electron deficient species, that means the species which are deficient in electrons, such species we call them as electrophiles. So these aromatic compounds, as they are rich source of electrons, they attract easily electrophiles towards them. Okay, so therefore electrophilic substitution reactions are common in benzene as well as the other aromatic compounds. So what's the topic? Mechanism of electrophilic aromatic substitution. So this class particularly, especially, I want to show you how this electrophilic aromatic substitution takes place, that is the mechanism of electrophilic aromatic substitution. So students, electrophilic aromatic substitution, generally we find it takes place or it involves 3 steps. First one is generation of the electrophile. Second one is formation of the intermediate, that is carbonium ion, and third one is formation of the final product. Okay, first one is generation of the electrophile. Where from the electrophile is coming? For example, if we take a reagent X, Y. Okay, so this is the bond. What is the meaning of this? That means there are 2 electrons. Okay, so I am showing the electrons like this. Okay, so X, Y. If Y is more electronegative than X, then this comes out with the 2 electrons, leaving X plus Y with the 2 electrons. It gets negative charge. Okay, now this X plus is called as electrophile, and Y minus we call it as anionic species. Okay students, now this is the first step. What is it called as? Generation of electrophile. So from XY, X plus, when it is formed X plus, when Y comes out with the 2 electrons. These 2 electrons are present in between X and Y. So Y with its, as it is highly electronegative, it can attract or it can take up the 2 electrons and it can form the anionic species. And X plus is the electrophile. Okay students, this is the first step. What is it, ma? Generation of electrophile. So students, second step is formation of the intermediate carbonium ion. What is the first step? Generation of the electrophile. Okay, so once this electrophile is formed, now it slowly approaches the benzene ring. Okay, on the approach of the electrophile, what it does, the benzene ring. Look here, I have written the benzene structure and written one of the hydrogens separately plus X plus. X plus is the electrophile. Now this is moving towards, or this is coming towards the benzene nucleus. I told you why this X plus is coming towards the benzene ring, because it is rich in electrons. Okay, now this is deficient in electrons. Okay, so therefore easily these compounds attracts the electrophiles, right students? Now as this approaches the benzene nucleus, benzene undergoes electromeric effect. Electromeric effect. What does it mean? Look here. There are 3 pi bonds inside. And I think students, you must be knowing this pi bond is not restricted to these 2 carbons. They will be moving inside. That's why we say delocalized pi electrons. Okay. Now, this X plus is coming towards the benzene nucleus. So, one of the pi electrons moves towards this carbon. Okay, so this, suppose give the number students 1, 2, 3, 4, 5 and 6. Fine. So these pi electrons will be shifted towards the first carbon. So now there is no pi bond here. 2 electrons shifted towards this carbon. That means this carbon gets negative charge and this carbon gets positive charge. Okay, once this negative charge is created on this carbon, it attracts this positively charged X. That means C minus X plus. There will be an attraction between these two. So X plus will be attached to this carbon which has negative charge. Okay. So I will show it here. Benzene ring. Okay students. See, this pi bond is here only. This pi bond is here. Now this is moving to this side. That means here a negative charge is formed. Here a positive charge is formed. So this X plus is attracted towards this carbon. So there is hydrogen over here. Now X comes over here and positive charge is here. This is called as the intermediate carbonyl ion. Okay. Now this positive charge will not stay here only. Okay. It moves towards the entire benzene structure. So next immediately this pi electrons will be shifted this side. Okay. That means these pi electrons will be coming here. Now this positive charge comes over here. Here is the pi bond. Here is the pi bond. Next here comes the positive charge H and X. Okay. Now this doesn't stay here for so long. Immediately what happens? This pi bond is here now. These two pi electrons will be shifted this side. Now this positive charge moves towards this carbon. Okay. So here is the pi bond. Here next positive charge H and X. Okay. So you can give them the numbers 1, 2 and 3. Okay students. So what is being formed here first? X plus, when it approaches benzene ring, it undergoes electrophilic effect by which one of the carbons is getting or acquires negative charge and the other one gets the positive charge. Okay. So then the carbon which is having negative charge attracts this X plus. That means there is a bond formed between this X and carbon. So this is what the structure that is formed. So this is called as the carbonyl ion or the intermediate ion. Now this positive charge is not static, it is not remaining or it is not restricted to this carbon. It will be moving throughout the entire structure. And you should notice one point students, especially this positive charge is concentrated here, here and here. What are these positions called as students? The positions adjacent to the carbon bearing the electrophile or the position, and this position is the para position. Okay, and these two will be, we call the position as meta position. Okay, so most commonly you can see here the most important thing, the positive charge is concentrated especially in ortho-para positions. So here what do we say? These three are the resonating structures. The carbonyl ion, that is the intermediate ion formed by the attack of the electrophile, is stabilized by these resonating structures. Now these three resonating structures we can represent by the resonance hybrid. Now you can see here students, inside the pi bonds are moving, so that we can show like this, and the positive charge in the middle, here hydrogen, here X. This is the resonance hybrid. All the three structures can be represented like in this form, that is the resonance hybrid. Okay, and also one more thing. This is the slow step students formation of the intermediate carbonyl ion. As you all know, the slow step will be the rate determining step. That means the step which determines the rate of reaction at which speed the reaction is taking place. So this is the second step, students. Okay, students. So that was the second step, and the last and final step is the formation of the final product. So we have seen how the intermediate carbonium ion is formed. Formation of the final product. So in the first step, X plus Y minus. X plus was the electrophile and Y minus was the anionic species. Now in this third step, we see the anionic species, that is the Y minus. It abstracts the proton. Look here, students, how I am drawing this arrow. Okay, so I am not touching the bond between carbon and hydrogen. That means H is coming out as H plus Y minus. It is a HY. Now what happens to these two electrons? They move towards the inside the ring. That means the two electrons go inside the ring. Therefore we get the 3 pi bonds, and now here is X plus HY. So this is the substituted product, and H is being substituted by EX. Okay, students, understood? And you know, so while teaching these organic topics, I am super excited. I don't know about how you are feeling. Okay, students, I am enjoying. You know, I'm having a tasty, delicious food like I'm feeling. Okay, so how you are feeling, you just comment in the comment section, and don't forget to, students, so before concluding, I want to tell you, this is the general mechanism of electrophilic aromatic substitution, and in the coming classes or in the coming videos, I will teach you taking few examples. So this is generally we have seen, right? So taking few examples, I will help you out how the mechanism takes place. Okay, so if you like this after watching, don't forget to like the video. Next 3 points you should remember. Like the video, next comment the video, share the video, and the final one, fourth one, those who have not subscribed yet, you have to subscribe, because you may not miss the videos which I am uploading on the channel. So that if you subscribe, you will be getting the notification. Don't feel like bored every day I am saying this, but you have to subscribe and also introduce this channel to your friends, whoever is studying in other colleges, students. Okay, so thank you so much for watching this topic, and if you like this, you just write down in your notebooks. Fine, students? Okay, so this is all for today's class or today's video, and have a nice day, students. So you have to stay home, stay safe, and take care. So here's Afia ma'am signing off. Bye-bye.